Okay, made it back. One more weekend, starting up week number 3. This week, the main thing is trying to finish up homework 1. As a quick logistic reminder, there's no penalizations for late submissions, but I do ask if deadline is coming up, it's what is the 12th? In my head, when I planned it all, I had a plan, but now I'm trying to remember. Thursday, there we go. So Thursday night, it's 11 p.m. and you're still trying to finish something, but but I need sleep because there's also midterm 1 of 5 in one of my other courses. It's totally fine to just say I need some extra time, and just that is your submission. Just let me know 2 things. Of 1, when are you turning it in? How much longer do you need? A day or 2, you never need to wait for a response. If it's going to be 3 weeks or 5 weeks for some reason, maybe that would happen. But now you're going to be multiple things all piling up, and that I would rather not happen. So let me know when it's going to be in, and then the second part is if you need help, then what help do you need, or how are you reaching out? Are you going to TA office hours, coming to class the next day, and you just want to talk about how to get something done, anything like that? Just as we're getting into the flow of submit, start a new assignment, move on to the next module, all that, or the project, all this process. Cool. That was the question that nobody asked for the morning. And what questions do you actually have that you want answers for? Did you break anything? Is anything interesting happening that you didn't expect, or something that you did expect and you just want to brag about it? You set up your FizzBuzz, and the first time you ran it ran exactly right, all from scratch. Your computational mechanics. Nothing to start, at least nothing to kick off the day. Not yet. All right. Let me check in, see where people are at, and then we can jump off from there.
Starting to like talk and get thumbs up and how to say like things. It still sounds like exactly like you translate. Friday. Saturday when we got back, we went down to my wife wanted to do that before she left for her conference. It just couldn't schedule. So we did that when she got back. Sunday was just a lazy day. It was show you here. You don't get to choose these. There's something public like great. So
This one last time I didn't change a single thing. I'm just saying.
This is like a soup. It's a very common rate on error that's all powered on. You can get code somewhere else. Translate it right. Easy to come on.
I saved it. It doesn't file. But it's a rate thought process. Like every time you expand it by one column, it should be one thing faster or one thing slower. The big thing is usually the MVP. It's just a ton of
So how does that feel?
I really don't know.
Meaning there's like an extra something lost. But now you've got 3 data points that you can so whenever the brackets are around that XY, that's saying those are optional. So if you remove the brackets, you're giving that Y. Oh, it should be PLT dot. At least I think there is a contour built. Yeah, that's like baseline. Every color is one like band of numbers. So right now, the smallest number is 0. 0 times 0. It's all 0 here.
color and same thing. That's usually like if you see like stress diagram, it's also this one says like one has before it said
So I was as one does, and so it was like it was so funny where it downloaded to OneDrive, like personal OneDrive, and it just is like it pretty much was like zip on.
I'm gonna say, wow, they tell us to one better.
Just decided it was just like this is where I need to go. So it's zip on, man.
I'm doing like that.
No, it's not. It got it was well over capacity.
Mine's over. It's like a year and a half.
Yeah, OneDrive was just like your OneDrive is 170% capacity. It downloaded like all of the just like all the language files and so I was like Solid?
Yeah.
Solid worked fine now. Like not from the run. I never tried it, but it was like yeah, just I got solid with some
so like this is the line that
Random.
Solid.
I can access it from any device.
and it's like on my transport because really it's like one word right there, but it's showing you that someone between this axis and that axis change from zeros into one through
But this can be zero, right?
yeah.
Not made of distance. Yeah.
No. So sometimes it makes like these kind of contours sometimes are helpful. Like if you had numbers on them, but like contour F shows you ranges. So now this is like 0 through 0 to 18. That is all in dark blue band. And if you want to know what it is,
Oh no, you do it.
0 to 15 and years.
Yeah. Well, it depends when you this one has like a curve. Like if you ask for the input,
Yeah, like all of these are one of your X line.
yeah, it's like someone else and that's it.
All right, so let's hop into questions that we've had so far. So sine, cosine, seemed like we were getting some nice work in there. But then coming down to oh, there we go. All right, so there were some like clarifications of like contour plots. Like, what are they? What is it showing you? What does this mean? Like, what are the colors? And like, if we look at the data that it's actually plotting, it's kind of like a whole bunch of zeros along. Kind of have to flip this. I think take the top, put it at the bottom. Is that right? Yeah, that's what I'm thinking of. It's kind of weird. It's like a picture, like pixel 00 in a picture is like the top left corner, not the bottom left corner. To like mirror symmetry from along the x-axis. But anyway, so x and y-axis. So there's a bunch of zeros, and then as we kind of move diagonally down, it's getting biggest, like the steepest increase, and then this way and that way, or less, like along the x or y axis. Different. So when we're looking at like a contour plot, and I personally like filled contour plots because it shows me like for a given band, what are all the equal band, like what's all the stuff that's close to each other. And this would be similar to like finite element like stress diagrams. That's why like looking at a contour plot like this is kind of helpful when we're just looking at some math. And someone pointed out as we were looking at this that it's every one of these like contour lines is a 1/x line, because that is the line where it's constant in the multiplication table. And if we want to know, like, all right, well, what is dark blue versus big yellow, we can say plt dot color bar, and then start looking at like, all right, dark blue is 0 to 15. So this line is kind of giving me my when is A99 equal to 15, and it's interpolating between values. But I mean, 3 times 5 is 15, so we do have some values there. And then 30 is going to be that line, so it's giving you like the bounds on those colors. If you're like, well, that's not enough colors, I want more levels. And I forget how to do the levels. But we can always ask. We can say like, help. Levels. I think we just give it a number. This is my hack for the documentation. I scroll all the way to the bottom and look for examples. Oh, and this one doesn't have one. All right, so let's go. Does this one have examples? No, no examples. All right, anyway. Levels, we can either give it like an array of levels of saying like, give me 0, 10, 20, 30, 40, or we can just say like, all right, split it up into 100 levels. And it should just be the next thing. So instead of 5, right now we've got 1, 2, 3, 4, 5, 6 levels. Let's look at 20. Bigger is better, right? And now it takes those same colors and splits them up into more like evenly spaced kind of things like that. Oh, it'll catch up in a second, but now like smoother gradient going that way. That one was, this was something that came up as I was talking to people, just like FYI, like what are we doing here? What is a contour plot? Technically, if you can write this one line of code, then you have done like what was asked of you, but it's always nice to have like, why? Like think about the why. Why are we doing this? And it's cool because now you can have like these kind of plots are way more impressive in a senior design presentation than like I don't know, like Excel generated sort of bars and stuff. All right, so then another thing that came up was really just kind of like general, like how do you debug code? So if I like run, if I just copy and paste that function and run it, nothing happens. I get no error, everything seems fine. Because all I've done is say define this code, and it hasn't. Python is, again, this is kind of a quirky thing about like an interpreted language like Python or MATLAB, is that it doesn't check the code that you put in a function. So when you define a function, you can put as many errors in that function as you want, and it's not going to hit that error unless it actually runs that piece of code. So the next step is like, I have to try to run this, which means I have to try to understand what this crazy professor was actually trying to get me to do. So I'm having to like read this lin interp function, like what is he talking about? What is, can't even spell linear interpolation, it's interpolation. So there's already, like, there's just something wrong with this guy. But let me just try it. Lin interp. And I'll say, like, x is 1. And if I want to, like, document for myself, like, what's going on, I can specifically, like, set a variable as x equals. And then p1, it's like, all right, this guy wants some kind of array. Like, all right, let me give him some kind of array. And I'll say 0 and 0, and then P2, I'll put this as another array, and put this one as like 10, 5. Then once if I can figure out like the inputs that I'm supposed to get, now at this point, I'll get an error that, did everyone see like an index error, an issue when you were trying to run this first time? Index 2 is out of bounds. Expand this out. And again, if you're starting from the top of the error, it's showing you exactly what call caused the error. But if you start from the bottom, it's showing you like the root cause of the error. So down here, it's saying on this specific line, when you tried to say slope is this, not you specifically, but your insane professor, so he said slope was this, and I can't do that. You're getting an index error because it's out of bounds. I'm like, well, what does that mean? And P2 is the first thing that gets called, so let me try that. P2 of 2, and it's still giving me index error, but now I've like, now that root cause is getting smaller and smaller. Like it's not just that the function itself is wrong, but this specific call to this specific part of the function is wrong. And then I can say, this guy grew up in the days of MATLAB, when MATLAB was a thing, because index 2 is in Python is really the third index of a thing, because it goes 0, 1, 2, not 1, 2, 3. So, all right, it's crazy professor. I got to go back and refactor all of his code, change all these off by 1 errors. So anytime it says 2, really I want 1. Anytime it says 1, really I want 0. And then, that one's 0 and a 1. So when I fix all this, now when I look for what is y when x is 1, I get 1/2. And the slope was 1/2. I chose a case where I would know something about it. And I'm getting what I expected now. and even if you went through this already, like maybe you quickly kind of saw it, fixed it, moved on, that process, a lot of times that process of like, what is the root cause and kind of, and that's the nice part about having an interpreter or like a Python or a Jupyter thing to run is you can try little pieces of code at a time and see where that error is coming in. Also, you can see like what are the when this variable gets defined, like what is it, like what is it supposed to be, how does it look? Yeah, and I think those were the main things. Did anything else come up as we were looking at those problems? What other questions did you have? Good for now.
So we're doing 2 solutions for us. We're doing it in the preliminary version.
Oh, in the next part? Yeah. Okay. That one, I wasn't sure how many people were here, but we did have like a little conversation about this. All right, so in this problem where we're kind of we're starting to look at like this, the reading in part 3. This is really like the newest thing that you've probably seen, at least in this course, because a lot of the other stuff was kind of like a reintroduction to Python and just getting comfortable with Jupyter and like using code, executing code. But now in part 3, it's more asking you like, what is an error? Like when a computer has an error, it's not the same as like a baseball error of like it dropped a ball. It's like it's a very defined thing, and it's always like something minus something else. So one way that we can look at error is just plotting things, and if one line is different from the other line, then we know that there's error. If we can't see a difference between the lines, then we probably can't measure a difference. Like we couldn't go send out another survey in the year 1940 and get a better estimate of what the population was. So what we're trying to do is compare 3 different results. One is like actual measured populations. What was the recorded population in these years? And then an Euler approximation of like if we're saying that the change in population is always proportional to something times current population, and then numerical integration. And then since that's an exact differential equation, we can also like integrate it and find an exact solution. So we've got 3 things that we're trying to plot. So next we want a PLT plot of like T and P Euler, and then another T, and then it'll be like pop 0 times exponent of K, what do we call it, KG? I guess we can call it whatever we want, right? So in this, and I'm just using some comments just to say like, this is what I want to do and make sure that I'm ready to do that after I've defined my independent variable time and my dependent stuff. So in this first line, or sorry, in this third line where I'm plotting like an exponential growth function, the only thing that I need is k and t for that. So I could directly define t, that independent variable, and then be done. A range 1900 to 2021, time steps of 20. And if I have a function like that, there's no convergence, right? Like we don't have to worry about, I mean, we have to worry about round off error, but there's no truncation error because it's just, the function is the function. Like that is the solution. So now I should be able to look at like the actual like dots, which are, or squares, which are world population versus my like analytical solution, which is some curve. They both start at the same exact value because that's like what my initial condition is. So they should be the same. Otherwise, I did something really off. Now I just need that Euler integration. And before, so I could just code it, but let me see like who's working on this and how you went about it. What were you working on for that Euler integration? Were you working on this one at all? Did you finish it? Were you working on this Euler integration? Not yet. Oh, you're using. So that would get you to connect that last line. Like that would be like actual analytical. Yeah. So this is like a difference. Yeah, this one's different. This one's like numerical. I'm going to predict the next value based on the current value. So I should only need like the right hand. So when it says DBT is KP, I don't need DBT. I should just plug in that KP. Yeah, so timeout's gonna something away. Don't time like print statements. Okay. Because those, and there's two reasons. One is that it gives you a valid output. Yeah. And then the other part is that it's always timing how long it took for the system to call room and then switch it onto. We don't really need that. Yeah. Compare times of things. Oh, yeah. And I think it takes oh, yeah. Along with the analytical solution. And yeah, how did you do Euler? So yeah. So each time step will calculate the derivative of the function, and then it takes the change in time we want and multiplies it by the slope and the current value. Why is the slope? Why is it
this is an example. Slope is yeah. I think we'll do. I think this. It should be right? No, now you're saying that the slope is KP e to the t. So you're adding. So usually the first time people do this, they usually do that and try to solve it. Pre-solve solution to integration. But it's usually take out those brackets around x1. Because that's a notation to say like, oh, it's optional.
Sometimes there's a bit of like magic behind like there's nothing up my sleeves because as I just jump right into coding, it seems like wow, he's so good at coding, but it's like really like I've done the problems a lot and I've like thought about what I want before I start typing and programming and all this stuff. So let's do like back to drawing board of like if I want to do a Euler integration whiteboard approach. Let's see if I can catch up. Then what this equation is telling me is that the change in population is always proportional to current population, kind of like a bunny's multiplying. So the more bunnies you get, and people. So I'm going to forget everything I know about calculus and differential equations and say that the change in population over the change in time, like an actual, like a delta, no longer a dp dt, but an actual change in population next year is minus population this year, kind of equation. So let's do like population 1920 minus population 1900 all over 1920 minus 1900 is k times the population in 1900. And I'm writing it out this way. So I don't whenever I'm using like a computer to solve differential equations for me, I don't want to do any like calculus. The goal is take all that like fancy calculus that we learned, just flush it, and the only thing we want to do is math, like just adding, subtracting, dividing, and that's it. So now population of 1920 is k times p of 1900 times 20 years plus the population of 1900. And this gives me like one prediction. But if I want to predict population in 1940 based on 1920, I can add 20 years to each of these, and it's still going to be a 20-year time step. So I can change this into like population of I plus 1 is k times population of I times 20 years plus population I. So I'm taking my differential equation, getting rid of all the fancy differential part, and just calling it like next population is current times k plus current. And this whole thing here is dp dt times delta t. So the slope times a time step is how much I'm gonna grow. And I could use this, I could skip directly to this formula if I wanted, but Euler is easy enough. All right, so now we want to know, how do I actually do that? Well, first I'll set up what's called initializing my array. Same thing that we did for A99. At least some people did that for A99. Just set up an array full of something that you want to solve for. Zeros, and for every point in time, for length of t, I want a 0 put there, and then I'll fill them in as I go. So then that P Euler, my first population, I don't need to solve for that because it is a population at 1900. So use that population, pop 0, just have some initial condition. And what do we want to do? So we'll start at 1, go to the length of t, and now my P Euler of I. What is the, so P Euler, as it catches up with us, P Euler of I. Yeah, do we want to do I plus 1? All right, let's keep it the same, right? Start at 0, go to length of t minus 1. So let's do I plus 1. Just so we have, what I wrote on that side is the same as over here. So what is my right-hand side now? What I wrote there. So what does that look like? Yeah, but like, what? Let's say that. K. P. Yeah, pop. What variables do I want to put in there?
P, I.
P. I. Times that 20. Really, I like to have, so if I change it, anyway, just refactoring a little bit, and then add what? P Euler I plus 1, I minus 1.
P Euler
Of I. So the same, so whatever, at least for Euler, whatever index I have here, that's what I'm adding over to the next one. There's other ways of integrating, and we'll look at those like module 3, but the very first introduction to like, how do I use a computer to solve differential equations? This Euler is like your best first approach. Like, and if Euler works for you, then leave it at that. If not, then import some solve IBP functions. Okay, so now we have P Euler. Let's do this one in like blue. We'll do green. We'll do dash dash. All right. It'll catch up in a second, but we have 3 lines. Euler in green, And I can add labels to these. That would be better, which I'll show you in a second. But one of the questions for the homework is like, if I change DT, so right now it's 20 years. If I make it 10 or 3 or 1 or 1/2, if I integrate it more often, what's going to happen to that green line? Where's it going to go? It goes up. Yeah. Where's it going to stop? Where, like, if it converges to something, is it going to converge to any of these blue points? So that analytical, yeah, because so we can converge to analytical solutions, but it's not necessarily going to converge to like experimental measurements. Because normally, if we're solving a differential equation, we're kind of smoothing out a lot of other stuff that's going on. And if you want to see that actually happen, go from like 2 to 20 years, or 20 to 2 years. And that green line is now, and again, it'll catch up in a second, but green line goes from a few million less to now almost the same prediction. And again, this is graphs are a great way of saying like, this is the error, or there is no error, because you can plot the two, and if the pixels can't show an error, then there's probably not an error, unless you need to put it on a log scale or something. Cool. Thanks for sharing. I think, yeah, that is our time. We'll be back Wednesday, try to wrap up homework 1, and then Friday start up project number 1. Yeah. Yeah. Like to that little block. Yeah. Yeah.
That was like 1.3.